everyone. The purpose of this video is to introduce you to thinking about a graph dynamically, which is different than thinking about a graph statically. Take, for example, the data that shows the number of confirmed COVID-19 cases in a given day. Now, if you are interested in static information, you may ask, how many people were confirmed infected on August 18th, 2020? That's an input, and then you would get an output. If you were interested in reading this graph dynamically, you would say, how does the number of confirmed COVID-19 cases change over time? Or how does the number of COVID-19 cases increase or decrease as time passes? Let's start out with a slightly simpler example that we've already looked at. Let's consider the graph of the share of the population living in extreme poverty. Now, this graph is not the United States graph that we looked at last week. It's a graph that uses the countries that are already populated from the Sustainable Development Goal Tracker. Now, if we look at this graph, to read it dynamically, we want to read it from left to right, and we want to look at how the share of the population living in extreme poverty is changing over time. Another way to put that is, how does the percentage increase or decrease as time passes, as time increases? So what we can see with Bangladesh is back in about 1983, the share of the population living in extreme poverty was about 30%. It decreased till 1985, and then it started increasing. Now, this point where the share of the population living in extreme poverty goes from decreasing to increasing, mathematically we call this a local minimum. Then the population increased, but then noticed that it increased steeper in the late 1980s and then kept increasing, but increased slower in the around 1990s. And then there was a peak at around 1991, and then the share of the population living in extreme poverty in Bangladesh started decreasing. This point where our share of the population living in extreme poverty went from increasing to decreasing, this is called a local maximum. So then we have it's decreasing. The share of the population living in extreme poverty is decreasing. But then notice that it is decreasing faster in the early 1990s than in the late 1990s. So it decreased faster and then kept decreasing, but at a slower rate. The nice thing about looking at data like this is we have these little line segments that are connecting all the data. So you can very clearly see that if you think of each one of these segments as a line that has a slope, then the slope here is going to be higher than here. And the magnitude of the slope here is going to be larger than the magnitude of the slope here. So we can do that for any graph. We can talk about how the function is increasing or decreasing as we increase our independent variable. We can also talk about local mins and local maxes that occur when we either change from increasing to decreasing or decreasing to increasing. And we can talk about how steep the graph is when it's increasing and how steep the graph is when it is decreasing. We will be formalizing all of these ideas this semester, but these are the general ideas behind a lot of what we're going to unpack. Where does our function decrease? Where does it increase? Where do we have local mins and maxes? What do they mean? And what does it mean if it's increasing faster? in some part of the graph than another part of the graph? And how do we quantify that steepness? Let's go back to the coronavirus data. So what you can see in the United States is that there was an increasing number of cases back at the beginning of the epidemic. It looked to be growing about exponentially, and the function was getting steeper and steeper and steeper. That means the number of new cases was climbing faster and faster and faster. Then there was this point when the number of new cases stopped increasing faster and faster, but still kept increasing. We say that the number of cases was still increasing, but at a decreasing rate. That's when we start to think we're going to get to a local maximum. And back at that time, it was very interesting because when we hit what we call an inflection point, when we change from increasing at an increasing rate to increasing but at a decreasing rate, when we hit that point, that's when everybody started to act like the pandemic was over. It's very interesting. They were acting like they were at the peak up here, but actually cases were not going down, but they weren't increasing as fast. If this feels overwhelming, we're going to unpack this all semester. We're building the language and the ideas first before we do the calculations, but that's just so that we get a lot of exposure with thinking about these ideas. Then the number of cases started to decrease. And notice that it was decreasing at first, not very slowly, quite radically. And then it dipped quite a bit. It decreased quite a bit, and then it kind of leveled out. And then the number of cases started to climb again. And again, initially it started out as exponential growth, but then it kind of leveled out a lot and had this kind of constant increase. And then again, the number of cases kept increasing, but they were increasing at a decreasing rate. What that means is our graph here was becoming less steep. Then we hit the peak, and now we're on our way down. Now, hopefully, we keep on having the number of cases decreasing. And we can unpack what was happening in different states during this time. But for right now, I want you to focus on the following. It was increasing in certain regions for certain days since the first number of cases were confirmed. It was decreasing for other days. And then there's a difference between increasing when the graph is getting steeper and increasing when the graph is becoming less steep. Looking at data is a little bit challenging because we get a lot of this up and down and sharp edges, which we really don't want to deal with calculus, and you'll see why as we progress this week. So what I'm going to do now is move us to our functions that we looked at last week. And we're going to go through each one, and we're going to talk about the function in this dynamic way. So let's go ahead and graph the first algebraic function. And what you can see is this graph is decreasing, but it almost looks like a line. So we say it is decreasing at a constant rate. Then it becomes less steep. We hit this minimum and our local minimum, and then our function starts increasing. And notice that here it's getting increasing and it's becoming more steep. We say that's increasing at an increasing rate. And then it levels out and seems to be this constant increase. Notice that I'm reading this graph from left to right. It doesn't matter if I'm in the negative x or the positive x. I read it from left to right because I'm talking about what happens as my x is increasing. And so as we move along, sorry about that. As we move along, our x is getting bigger, and we're interested in what does our y do as our x is getting bigger. And we might ask, what is our y as x is getting bigger? But we also might ask, how is y changing? All right, let's look at the next algebraic function. Notice that we start at about x is equal to 0. It's undefined there, but we start there. And our function is increasing. It's a little bit hard to see from here. Let's go up here. It's increasing, and notice that right away it is increasing and it is becoming less steep. we hit this local maximum, and then our function, right, is decreasing. It goes from increasing to decreasing, and it is becoming more and more steep. Then, somewhere in here, Desmos sometimes can find the point for me, somewhere in here, it starts becoming less steep. Again, that is called an inflection point, something that we will come back to. But notice that everywhere to the left, my function is getting steeper. But then everywhere to the right, it is becoming less steep until we hit this local min, our local minimum, and then our function starts increasing again, and it gets steeper and steeper and steeper and steeper, and it seems like it keeps getting steeper. All right, let's look at our cosine graph. Our cosine graph, as I mentioned last week, cosine is periodic. It repeats itself every 2 pi, which is just over 6.28. So what happens is if we start, let's just start at x equals 0. We're starting at a local maximum, and then our function starts decreasing. It starts out less steep, becomes more steep. This is the steepest part of our graph, our inflection point, and then it becomes less steep until we get to this minimum, this local minimum. And then the graph starts to become more steep, hits the steepest part, the steepest point, and then becomes less steep. And this repeats itself because when you have a function repeating itself, the dynamics repeat itself. How it's changing repeats itself. The sine graph is very similar. I'm not going to go through that one. But instead of starting out at a max and going down, it starts out increasing. Now, let's go to an exponential function. An exponential function is always increasing, or I should say an exponential function with a base that is bigger than 1, is always increasing, and it's becoming more and more steep. Now, one of the defining features of an exponential function is that the steepness of the graph actually depends on your output. So the steepness here depends on this 4. The steepness here depends on this, what do we have, 7.5. So the exponential function gets steeper and steeper and steeper, and it is increasing. If we have a base that is less than 1, let me quickly put that in. Then what we see is the function's always decreasing, and it becomes less steep. And it keeps becoming less steep. Now, I'm going to keep this exponential function on my graph, and I'm going to add the log base 2 of x. Now, on first glance, these two graphs look very different. But when you read them dynamically, they are both increasing. My exponential function increases. My logarithmic function increases. However, the biggest difference, except for just the domain, the biggest difference is the exponential function increases and gets steeper and steeper and steeper. My logarithmic function increases, but becomes less steep. And visually, these are very different. If we are talking about a pandemic, would we rather our number of cases grow exponentially or logarithmically? I think logarithmically is the answer, right? Because it means that our number of new cases is still increasing, but at a decreasing rate. So these are ideas that we are going to formalize this semester. Rather than just talk about increasing or decreasing or increasing steeper and less steep, we are going to determine metrics for that steepness. And we are going to unpack a big idea here that is about the instantaneous rate of change.